can't think as people do. The machine is different.
Being! What marvelous being! How gratifying! How gratifying!
Thank you for coming. We'll see, maybe I'll be a little closer to you than I might have been. So, I'd like to start by just talking about some history of artificial intelligence and computing itself. So electronic computers, as you might know, were a World War II effort having to do with breaking code that the Nazis were using. One of the critical people in this effort was Alan Turing, and his picture is up there. One of the things that's interesting to know is that in the 1940s, if you used the word computer, you were actually talking about a human being. So that was a job description like being an accountant. And that affects some of the nomenclature that gets used for these sorts of fields. And Alan Turing was an absolute genius. In his 1950 paper, he, what's the right word? He envisioned artificial intelligence and envisioned machine learning that computers would be adapting as they ran. And so in the 1950s, Alan Turing's genius, when computers were brand new, was able to envision these things that we start taking for granted now. Oops. So we're film goers, so I put, this is, if you think you know what Alan Turing looks like, that might be what you're thinking of. In Turing's paper, he devised a game he called the Imitation Game, when he was imagining that in someday we would have a conversation about whether we could say computers were truly intelligent or not. And he imagined the different arguments that people would make about why the computers were not really intelligent, and came back with answers for every one of them. But the basic idea of the imitation game is that if a computer could pretend to be something it wasn't, there's a funny spin on this game actually, it was sexist. So a computer had to pretend to be a woman, and a man had to pretend to be a woman. So both of those things were pretending to be something that they were not. And if a human judge could not discern whether it was the man or the computer that was pretending to be something different, then by Turing's notion, you would have to concede that the computer was intelligent. Turing in that 1950 paper coined the term machine learning, which is what we say when we're talking about computer programs that adapt as they run. And that again goes back to, you wouldn't say computer learning because that would be a human. So we would often call them computing machines, and that's where the term machine learning comes from, is again Alan Turing's genius. And I think even the term artificial intelligence might have been different. It might have been called computer intelligence, which might have been a little bit more of an accessible term. But machine learning in particular is a very awkward term. And I like to explain it because it's all due to Alan Turing. So we'll now talk a little bit more about modern artificial intelligence stuff. In general, artificial intelligence refers to programs that are smart in some way. The grand goal of this is the AI programs that we see in the movies. And of course, we're not there yet, but that if the computer program can be mistaken for human, then following Turing's idea, then we would concede that the computer program is intelligent. Talking about, so this is a still from the movie that you'll be watching. In the 1980s, so we can't get all the way to that human level intelligence. Let's walk our way up to it. One of the observations was that smart people play chess. And so if we could write a computer program that could play chess as well as a human being, that would give us some insights into what intelligence was all about. And so this was a large endeavor in the 1980s to do things like play chess, do things that smart people did, even if we couldn't solve the whole problem. And early chess players, as in the era of the movie, were constrained quite a bit by just the hardware capabilities. So on the one hand, we have the grand goal of human intelligence. more modest goals, often when we're talking about artificial intelligence today, we are talking about just being clever about a certain way to solve a problem, in the sense that most computer programs we know how to solve the problem, and we just have to write the program to march through the steps to do that. Artificial intelligence, the problem that you're trying to solve is so big that we human beings don't know how to program it. So we write a computer program that can, we use the word search, can search for a solution to the problem. And I'll talk a little bit more about search in a moment. Then here are some different board games and some history of playing them over the years. So again, electronic computers were in the 1940s. As early as 1959, Arthur Samuel wrote a checker player and published a paper on this that also did some learning, actually. So that was an early success of board games and computing. And you can imagine in 1959 how constrained the computing resources were. You have probably heard of Deep Blue and winning a game against Kasparov in 1997. So that was a success of a chess player. And then just the past 2 weeks, there was a Go tournament. AlphaGo, made by Google, beat the human player 4 out of 5 games. And Go is considered an enormously complex game. So one of the things to think about, like, how do these board game players work, and this idea of search. So Tic-Tac-Toe is much easier to think about than some of the other things, so let's start there. We start with the blank board, and if you're X, you can say that you have 9 different places that you could move, but we could also observe that if you put an X in the middle of a side, it's really the same move if you put it in any one of the 4 sides. So we can kind of condense this onto 3 different possible things that you could do. And as the notion of search is, I'm imagining what would happen if I played an X, and then I can imagine where you might put your O, and that would give us all these possibilities. And given those possibilities, I can think about where I could put my X and where you could put your O. And this is a small enough game that you or I could do it on a piece of paper, right? We don't really need a computer to imagine all the possibilities of this game. So this is comparing some of these other games that we've talked about. And I'm talking about the branching factor, so how many possible moves there are after each board position. And some of this just has to be rough because it depends on the configuration of the board, what you can do next. But for tic-tac-toe, there's about 3 possible next things. For checkers, there's about 8. For chess, about 35. And this, what's drawn here, is an illustration of what Go would be like, where it's just enormously branching. It's an enormously big problem to do this search problem, to look ahead and see what the possible games would be. So in board games, as I mentioned before, Samuel was actually using learning as early as 1959. And some of the things that he learned about, one is that he developed a scoring function that just looking at a board, you could say how good that board was for whichever player you're playing. And so he developed a scoring function to do that. It had coefficients on it, and he learned the coefficients to know which terms were more important to scoring the board well. And he also did just simple memorization because he didn't have the computing resources to do very much search. So if he'd seen certain boards, he would just remember the score that went with them so that he didn't have to keep searching from that point. Deep Blue, the IBM effort, largely the success of that program was largely due to massive computing power. So we talked about how big the search space was for that, and just having an awful lot of computing power to throw at that is the main reason that Deep Blue succeeded at what it does. And really it was a PR effort on IBM's part to a large extent to show how great their computers were. AlphaGo, this recent effort at playing Go, did some of the tree search that we were talking about, and also did what's called deep learning, which is sort of new terminology for what you might have heard of as neural nets, which is based on human physiology and the connections between the neurons. So a little bit, just to shift gears to talk about a different way of using computers to play games. My group has done some work with playing video games. So here we're trying to make an artificial player for the game, or if you're talking about a game that has multiple players in it, sometimes the same technology would be used for what's called a non-player character. So agent in the game that you're interacting with, and if it's done really well, you might not know whether you're talking to another actual human player or to an artificial intelligence player. And my group has done this with Mario, Miss Pacman, and a shooter game called Unreal Tournament. So with Miss Pacman, one of the interesting things about this game is the game Pacman, the way that human players are really good at it, it's entirely deterministic. So where the ghosts move are the same every time. And good humans just memorize a series of moves to make their way through Pacman. Miss Pacman is different. There's some randomization in it. So the ghosts move around, but they're not going to always be in the same place with a different playing of the game. So in this game, you can't just memorize a series of moves. You have to learn how to respond to the situation. So the approach that we use for this is called a rule-based system. For those of us who are not programmers or haven't encountered that term, there are rules that look, I'm in a particular situation, that means I should take this certain action. So some examples of that from Ms. Pacman are, if a ghost is too close to me, then I should run away. If there's an edible ghost nearby, then I want to eat it. And if there's no ghost nearby, then I should graze, which is just there's the extra little pills all over the board that you're supposed to clean up to advance to the next level. Learning that we did in this environment, one is similar to what Samuel's program did, is just to learn the importance of the different inputs on determining your actions, and also then just to learn these rules themselves of how to behave. Among the fun things about doing this is we were not very good Ms. Pacman players ourselves, and it wasn't very long until our game was playing better than we could. And as was mentioned before, we won an international competition for this. And again, there were two separate versions of the learning. And then similar setup, different game, Mario. So there's a level that you have to learn to play well, and the agent can learn just as we would. We play a level over and over and over again. We start to get better at doing it, and that's what the type of learning that this agent was able to do. So to wrap this up, so computer game playing has been around as long as computers themselves practically, and also Turing's notion of artificial intelligence and machine learning also goes back to the very early days of computers. And I guess I talked just a little bit about it, but some of the advances in playing the games now are because we are able to adapt and learn, and some of the advances are just because the computers are more and more powerful, and we're better able to deal with massive amounts of information. And that's it. Thank you.